Welcome to lecture number 11. In this lecture, our focus of study is on advanced pipelining concepts as well as superscalar processors. Over the last 10 lectures, we have seen how an instruction pipeline works, and in order to improve the performance of instruction pipeline, we are introducing few techniques that will enhance its overall execution speed up. Handling with hazards, handling with branches, and then how multiple execution works together, multi-cycle pipeline, everything we have handled. We will now focus our more attention into few of the advanced concepts in pipeline leading to superscalar processors. We have seen what a simple in-order pipeline is. The goal of pipeline was to complete one instruction per clock cycle. That was the idea of simple pipeline. This is a 5-stage pipeline where we are seeing in which an instruction is fetched every cycle and it is moved to the WB stage at every cycle. And we can see that every new cycle one more instruction is fetched, and in every cycle one instruction is getting over under ideal circumstances. Now, if you want to increase the depth of pipeline, then we have to increase the clock rate, and that concept is known as super pipelining. And the next stage is known as superscalar. When you fetch more than one instruction at one time, thereby we are executing more than one instruction in a time, and that is known as superscalar instruction. So, we will have a quick look of what is super pipelining and what is superscalar pipeline. Launching multiple instructions per stage allow instruction to execute with a CPI, cycles per instruction, to be less than 1. So, on an average I need only less than 1 clock cycle to execute an instruction, and that concept is known as superscalar pipeline. It is a bit tricky affair. We will try to see how superscalar technique is implemented. First, let me introduce you to super pipelining, where we are increasing the depth of pipeline by increasing the clock rate. So, imagine the previous scenario which has been shown by a bold arrow. This was the time that is needed for completing instruction fetch, and this is for instruction decode, that was your cycle. Now, imagine if instruction fetch should have completed in little less time, and then we are going to divide the pipeline into, let us say, 10 stages. Now, we can see rather than having 5 stages, now I have a 10-stage pipeline, and each of the stage is going to take even lesser amount of time. That means in less than half of the clock I can complete one of the operation. That means I could initiate more number of the instruction in the same given unit amount of time, and this is called the concept of super pipeline. For example, let us say our initial pipeline was working in 1 nanosecond clock. Now, if you are going to work in 0.5 nanosecond of clock, then means instruction fetch happens at every 0.5 nanosecond, leading to, and every 0.5 nanosecond one more instruction is getting over. This is called increasing the depth of the pipeline. Now, how can you achieve super pipeline? It is not that simple and straightforward. Whatever activity that we were doing, I have to find out that activity has to be subdivided into 2 equal sub activities, and that need to be done across all stages in the pipeline. So, instruction fetch essentially will be cut into 2. You just imagine like that. It is not possible to perfectly cut instruction pipeline into 2. Like that, if I could subdivide all the operation in our initial pipeline to smaller sub operations and then trigger the clock at that rate, and that will lead to super pipelining. Now, let us see what is superscalar. Now, superscalar pipeline is also known as multiple issue pipeline, where you are fetching and executing more than one instruction at a time. This means we have to expand every stage to accommodate multiple instructions. Consider this scenario. You have 2 instructions that are fetched exactly together, meaning I have to decode 2 of them together. Eventually, I will complete 2 instructions in one clock cycle. So, in every clock cycle, I am able to complete 2 instructions. This is called double issue. When the number of instructions fetched is eventually 2, I decode 2 instructions. I can make it to 4. This is called 4 wide issue. So, there will be 4 instructions that are going to get completed in unit time. Essentially, the number of instructions that are handled per clock cycle is larger than 1, and that will make you to operate on superscalar processors. So the word superscalar basically means if the CPI value, cycles per instruction, is less than 1, or IPC value, instruction that you can do per cycle, IPC value if it is larger than 1, that is called a superscalar processor. Your basic pipeline will give only a minimum CPI of 1. To achieve CPI less than 1, we need to complete multiple instructions per clock cycle, and that is what is known as superscalar. For facilitating superscalar processing, you need to have multiple functional units and a issue unit that is capable of issuing multiple things. And basically there are 3 approaches to handle this. One is known as statically scheduled superscalar processors. You are going to execute multiple instructions together, but which all thing to execute, that is been statically determined by compiler. So compiler has a big say in statically scheduled superscalar processors. Essentially, you have to run multiple instructions together, you have to fetch multiple instructions together, everything will happen multiple. Now, which all things will be grouped together, which are the ones that are going to be fetched together, it is determined statically. So, compiler has a big say, but it is not that a popular approach because of the overhead involved in compiler, and it is extremely difficult to find out the combinations that are to be run together. The second one, little wider used version is known as VLIW. It is known as very long instruction word processors, which we will learn in detail later. And the last one, most common one, is known as dynamically scheduled superscalar processors. Let us focus our attention to VLIW processors. In VLIW processors, we are packaging multiple operations into one instruction, and that is known as a long instruction word. Let me tell you, our normal instructions were like this. It has an opcode portion and then an operand 1 and operand 2. This is our conventional instruction. Now, when I talk about VLIW processor, you have a very long instruction word, out of which, let us say, divide into 3 different formats. This may be a load instruction, and this may be an ALU instruction, and this may be a floating point instruction. So, this may tell either it is a load or a store operation, followed by whether it is on R1, R2, whatever, and here it is the address portion. So, each instruction, each integer, each very long instruction word should have a load instruction, an ALU instruction, and floating point instruction. Now, what happens is all of them goes together into the execution unit. So, this instruction load and the ALU instruction and the floating point instruction work exactly parallel. For this to happen, there should not be any dependency between them, and it is the role of the compiler to bundle, to group instructions like this. This whole concept is known as very long instruction word. So, from a sequence of instruction, I have to find instructions of 3 combination each, or a group of 3 instructions together, which is known as instruction bundle as well. So, the instruction have a set of fields for each functional unit, that is what we have seen now. 16 to 24 bits is used per unit, and instruction length can vary up to 80 to 120. So, let us say this is my instruction, which is of 120 bits. Now, I divide them into 3 sets, each of 40 bits. So, my first 40 bit of my very long instruction will be part of a load store operation. The next 40 bit has to be interpreted by the ALU unit, and the last 40 bit has to be interpreted by the floating point unit. So, instruction length is very huge, which consists of multiple smaller instructions grouped together. Now, you should have enough parallelism in the code. Now, to understand that, so think of a case, whatever instruction that you get, all the instruction has to be grouped into this. So, any bundle that go, this is known as a bundle. So, any bundle need to have 3 entities. One should be exactly a load store instruction, other one exactly should be an ALU instruction, and the third one exactly should be a floating point instruction. Now, if you look at the concept of the bundle, for every program, it is a duty of the compiler to find out bundles. What if I do not have any load store instruction for the next 100 instruction? So, it is very difficult to fill up all the slots. So, that will lead to sometimes certain slots being unfilled or it is going to be empty slots. So, when I do not have a floating point operation, 1/3 of this particular long instruction word that I mentioned goes unused. This is a challenge. So, finding out enough parallelism for the VLAW word that has been already mentioned is also a challenge. So, there should be enough parallelism in the code to fill up the available slot and find enough parallel instruction by loop unrolling and scheduling. And generally VLAW bundles are formed whenever we do not have enough instruction within a single block, then you perform loop unrolling and do the scheduling such that I can use in VLAW. So, what are the disadvantages of VLAW processors? You have to find out parallelism statically, and all those instructions which are non-dependent can be run in parallel. And sometimes when there is no parallelism available between instruction, then the VLAW slots are going to be wasted. And since you are performing unrolling and scheduling, the loop unrolling is going to increase the code size, and you cannot detect hardwares in parallel because these are the instructions which are to be run together. So, all hazard detection had to be done at the compiler level. So, consider this VLAW processor where we have a load instruction where the value is loaded to F0, and then you are going to add F2 to F0. It is called a scalar adding, add a scalar value that is present in F2 to F0, and you are going to store the resultant in F4. Now, whatever is the result that is there in F4, you are storing into the same location. So, 0 of R1 is the location. So, ideally what we are doing, from the memory take a value into a register known as F0. Now, add F2 onto it and then you store back in the same location. That is what the operation is all about. And then since you have to repeat in a loop, you are going to decrement the value of R1, R1 equal to R1 minus 8, and then you check whether the value of R1 is equal to a loop or not, and then the loop is repeated. Now, consider the case that this is how your general program looks like. You have a load and then followed by an add and then store. So, all these three instructions are dependent. So, I cannot run them parallelly. So, there is no enough parallelism that is available inside this basic block. Now, consider you are going to work on a VLAW processor where each instruction bundle has an integer unit which can take care of branch as well, 2 independent floating point operations and 2 independent memory references. So, your very long instruction word VLIW has one is an integer unit, then you have memory operations, memory 1 and memory 2, and then you have floating point operation FP1 and FP2. So, an VLAW instruction, a VLAW instruction can have 5 components. So, it is capable of running 2 memory operations, 2 independent memory operations parallelly, 2 independent floating point operations parallelly, and an integer or a branch operation. Together all these 5 can work together. So, what is the role of compiler? From among the available program that you have, you find out 5 these components. There should be a integer or a branch instruction, and then there should be 2 memory instructions and should be 2 floating point instructions. All these are put together to form the long instruction word. But in the code that is been shown, there is one load, one ALU operation, then there is one load, one floating point unit operation, another one is store, and then you have a branch operation, and then you have an ALU operation. That are a total of 5 instructions given in the loop, and the loop is being repeated. So, it is very difficult to make use of 2 multiplication unit, 2 floating point multiplications unit work together. Let us now see how it is been achieved. We have already mentioned it is possible only with the help of loops. So, the same example, we are going to have a VLAW processor with one instruction of integer type, 2 independent floating point instruction and 2 independent memory reference instruction. This is the program we are going to perform loop unrolling. So, this is the VLAW pattern. See, you have 2 memory references. So, in one row is your one long instruction word. So, in each of the row there will be 2 memory references, 2 floating point operation and 1 integer or branch operation. So, what is the first instruction? First instruction is load. So, when I look into the first instruction, I can find out this is the first instruction, load F0, 0 of R1. Now, this load and its corresponding add has to be separated by one cycle. So, this is the add that will go. So, this is cycle number 1, cycle number 2, 3, 4, 5 like that. These are the cycles. So, there is a gap of one cycle which is already shown here between the load and the corresponding add. Now, once the add is over, it takes 2 cycles to perform the store. So, this is the first store. So, these add and store are dependent. These load and add are also dependent. That is what the dependency that I would like to show here. Now, since 2 memory references are there, if I unroll the loop for one more time, then you will get the next set of load F6 minus 8 of R1. And these 2 loads are operating on 2 different memory locations. I can say that they are 2 independent memory references. So, I could do both the loads together and both the adds also together, both the floating point add also together, because I can perform 2 floating point operations exactly same time, and that result in 2 stores coming together. Now, when you unroll again, this is the next set of values, which is acted upon minus 16 of R1 and minus 24 of R1, minus 32 of R1, minus 40 of R1 and minus 48 of R1. So, literally there are 7 iterations, and proportionately we can see that there are many add operations that is also coming, and if you look at each individual pair of load and the corresponding add, a delay of 1 stall is maintained, and between add and store another delay of 2 is been maintained. Since you unroll this operation of R1 equal to R1 minus 8, we need to do only once, R1 equal to R1 minus 56, because all other pointing to R1 are automatically taken care of by the loop unrolling, and then you have the branch statement. So, there is a stall between them. So, we can see that some of the slots are actually going idle, because there is not enough parallelism available. Even though I perform loop unrolling, many slots are going to be idle. But you can see that there are certain slots in which both the memory references are being used together. For example, consider this case. In whatever instruction that is issued in cycle number 3, I could perform 2 memory operations as well as. So, this is memory operation 1, this is memory operation 2 and 2 floating point add operations. So, essentially in cycle number 3, I am performing 4 operations, whereas in cycle number 1 and 2, I am performing 2 operations each, whereas here I am performing 4 operations. When I move to cycle number 4, I have only 1 memory operation, whereas I have 2 floating point add operation. Like that, wherever possible, we are trying to execute parallelly, and this whole concept is known as very long instruction word processor. So, essentially we took only 9 cycles, but if you look at, you could complete 26 instructions. One of the drawback is we require more number of registers. Of course, that is a byproduct of loop unrolling. Now, what is known as extreme optimization under all these contexts? We have learned a lot of techniques. Now, can we put all of them together? So, modern microarchitectures use triple combination, use dynamic scheduling, multiple issue that we have just learned, and speculation. So, use branch prediction, dynamic scheduling like Thomas-Rouleau's algorithm, and you make it superscalar. This is what you see in the latest processors that we are using in our systems. So, what are the challenges when you do this extreme optimization? You need to detect dependency between instructions that are issued in the same clock cycle. You are going to issue multiple instructions together exactly in the same bundle. What about dependency check between them? So, if there are instructions that are dependent, they cannot be issued in the same cycle. They should be part of adjacent or different bundles. So, dependency detection is a challenging task, and that has to be addressed. And then we need to perform register read for multiple instructions in parallel, and complex issue logic, because this dependency checking and hazard detection will make the issue logic little complex. And then before issue, we have learned in Thomas-Rouleau's algorithm, we need to book reservation station, and since it is speculation, we need to find out reorder buffer entries as a cycle. So, when you issue multiple instruction, you need to check availability of reservation station for multiple instructions and the availability of reorder buffer entries for multiple instructions. And handling multiple issues is always a challenge. Assigning reservation station and reorder buffer for every instruction that we are going to issue in the next bundle. Or limit the number of instructions of a given class that can be issued in a bundle. Like what you are telling that we can have only one floating point instruction permitted, one integer instruction permitted, one load store instruction permitted. And if reorder buffer is not available, of course you have to stall. So I was just trying to give a flavor of what are the challenges that an architect need to take care, or what are the challenges an architect face while going for the extreme optimization, handling of these dependencies, handling of the hazards, checking of the reservation station availability, checking of reorder buffer, all these are going to be a complex task. So all these issues are addressed in what modern day processors we are working on. So also we have to examine all dependencies among instruction in the bundle, and if dependencies exist in a bundle, you have to encode them in reservation station with appropriate reorder buffer entry. And then once you go for superscalar technique, you know that there are multiple instructions that are going to complete at the same time. So multiple complete or commit, that means multiple functional unit can produce your result exactly at the same time. So if multiple functional units are going to produce your result, then if there is only one bus, if the unit number 1 and unit number 2 are going to put the result together, then it lead to chaos. So the CDB, the common data bus, should be wide enough to accommodate results of multiple functional unit together. So when you have multiple fetch support, multiple decode support, multiple execute support, you need to have provision to accommodate multiple instruction values on the common data bus. Essentially that means we need to have a wider CDB. Now when you come to handling multiple issue, we need to issue only one instruction, one issue per instruction per unit per cycle, and wider operand buses are required because you need to fetch multiple register values together, and that means multiple register read, and then multiple instruction commit that is also being required. So essentially your CDB should be bigger, there should be multiple reading that should be done on your integer and floating point registers, and multiple commit also has to be done, and reading of reorder buffer as well as the reservation station also, there should be provision to multiple blocking. So consider this example what we have here. So you have a load operation, you are going to load an element into R2, and then I am going to increment the value of R2, and then I am going to store the value. So it's basically take a value that is present in the array, increment it by 1 and store it back, and then you go to the very next location and then check if R2 equal to R3, and that is a loop termination condition. Now let us see how to run this one without speculation. So this is the time cycle description of the task. You are going to unroll this loop 3 times. So these are the instructions that are part of first iteration, second iteration and third iteration. Now this shows when the instruction is issued, when the instruction execute, when memory access takes place in the case of load and store, and when are you going to write into CDB. So once there is no speculation, then that is CDB that is required. Whenever you write the result into CDB, that's a time in which the result is obtained. You take the first instruction, let us say I am going to issue in cycle number 1, then execution happen in cycle number 2. Since it is a load instruction, so what happens in the execution? In the execution stage, you are going to compute the effective address. So 0 plus R1 is computed. That happens in cycle number 2, and in cycle number 3 you go to the memory location which is given by the address 0 plus R1. So at the end of cycle number 3 the operand is ready, and cycle number 4 you write into CDB. Eventually you are going to write into R2. Now since I am using multiple issue, the second instruction also I am going to issue in cycle number 1, but I cannot execute the second instruction because second instruction is operating on R2, and that is a value that is available only at clock cycle number 4. So second instruction, even though I am going to issue at clock cycle number 1, it will start execution only at clock cycle number 5 because of the dependency factor. So this will happen only after this clock cycle. Since the first load instruction write into CDB at clock cycle number 4, the first add operation DA add DDIU, that is direct add unsigned integer, that will happen only at clock cycle number 5. Since it is an add operation, it is not going to make use of memory access, and once you perform the add on 5, you can write the result on 6. And now what about store? Store get issued on 2. So here the assumption is I am using a dual issue. At every cycle I can issue 2 instructions. So store also can be issued at 2. When you issue at 2, you can execute at 3. So computation of address happens at 3. And when are you going to perform the memory operation? Memory operation happens only after the result is available. So storing happens at 7, and there is no CDB writing as far as store is concerned. And then you are going to perform, since there is no speculation, I am going to run the loop, and prior to running the loop, my R1 values are adjusted. So that also issued at 2. When you issue at 2, I can do it at 3. Why both of them happens at 3? One is a memory operation, other one is a integer operation. So we have 2 separate functional units, both happen together. So when you do something at 3, I can write it on 4. See, now you see this instruction, this particular instruction which was issued at 2, it got completed at 4. But instruction store issued at 2, it is completing the store operation at 7. So clearly you can see there is an out of order execution. And once this is over, now I am going to have a loop, and remember one case, since all the loop statements are executed together in one slot, means even though it is a dual issue processor, wherein every cycle 2 issues are permitted, along with a branch, no other instruction is issued, because when it comes to branch happening or not happening, clearing or going back status during a wrong prediction, whatever, it has to be done. So generally you have to remember the fact that along with a branch, no other instruction is issued. So if I do a branch at 3, it is operating on the value of R2. So branch can happen only after the value of R2 is ready. And when will the value of R2 is ready? At this point. So the value 6, and branch can happen at 7. And now I am going, this is without speculation. When it is without speculation, every instruction that is coming after a branch, these one, will happen only after the outcome of the branch happens. So you know the outcome of branch at clock cycle number 7. Let us say going to the next iteration, these are issued at 4, one will happen at 8, 9, 10, that is computation of address, accessing memory and writing into CDB. Whereas the second one, 4, 11, why is 11? Because it's 10 to 11 dependency, and then 12 we are going to write back. If in the same way if you continue, I request you to go through the remaining entries and make yourself comfortable and thorough with what happens and what are the cycle in which these things are happening. This is an example without speculation. Now what will happen if I am going for with speculation? If it is with speculation, I am not waiting for the outcome of a branch. You can see there are entries after the branch also which are executed. We are going to write into CDB before the branch happens, but you commit only in order. So when you go for speculation, there is one more field that comes commit, and commit always is in order. So here also we have dual issue. You can see that 2 instructions are issued at any given point of time. Here also along with the branch, no other instruction is issued. So at cycle number 3, first branch is issued, cycle number 6, second branch is issued, and cycle number 9, the third branch is issued. And if you look at the execution number, you can see they are not in any sequential order. Some which are issued later will execute earlier than the other one. You can see that it is not in order. And the time at which they are going to complete also won't be in order. You can see certain instructions are completing also out of order, but the commit always happens in order. So this is an example of the code, that loop code with and without speculation. Now we move on to the concept of superscalar processor from a logical understanding viewpoint. So your conventional superscalar processor, what is given in the diagram is you have a RAM. You can assume that your main memory consists of 4 different programs shown by 4 different colors. Let's say green, red, yellow and violet. And each of the smaller boxes represent instructions. Now in superscalar what we do is, you are bringing multiple instructions together. And this is an execution core. It's a pipelined execution unit, meaning an instruction which is here, it moves to this unit. Like that, it takes multiple cycles for the instruction to complete the execution. So many execution units are there, are all connected. So you can imagine I am using a 4 wide issue, or 4 instructions are issued in a clock cycle. Conventional superscalar. So the idea is multiple instructions are fetched, multiple instructions are executed, and that's what happens. Now we are looking for symmetric multiprocessors. Let's say I am going to talk about dual processor. They are sharing the same memory, so the memory unit is common, and I have CPU 1, I have CPU 2. CPU 1 is taking care of the red program, CPU 2 is taking care of the yellow program. Both are internally superscalar processors. So you can see that I am fetching multiple instruction, I am executing multiple instruction, but it is symmetric. So two superscalar processors working together on a common memory, that is called symmetric multiprocessor. Now with this, are we going to come to the end of the ILP? No, we have tried our Tomasulo superscalar approach with reorder buffer, speculation, and aggressive branch prediction and multiple issue. That is the whole story all about. Tomasulo's algorithm is taking care of dynamic scheduling, speculations is handled by reorder buffer, and then you are using branch predictions to take care of control hazards, and now you increase the number of functional units to facilitating multiple issue. At very high issue rate, you can have cache misses because so many instructions you are fetched, and some of the misses will go to L2 and some of them can be off chip as well. We will learn about memory more in subsequent lectures. How to cover such long memory stalls that we will deal later. So we are going to deal with multi-threading whenever one particular processor or one particular set of program is encountered with misses. Can the processor shift to another program and run? So multi-threading allows multiple threads to share the same functional unit of a single processor in an overlapping fashion. So this is what is known as multi-threading. So far what we are dealing were conventional superscalar, and we are talking about one program at a time. Now look at the case. You have your red program, that is program A, and the yellow program, program B, both are brought together. So you bring multiple instructions of A in this clock cycle. Next clock cycle you bring multiple instructions of B. So you decode multiple instructions of A. So this is the decode unit or the issue unit. If you look at horizontally, either it will be white, that is the empty slot, or it will be red. Red means you have instructions of the red program that is currently being issued. So either it is a red in a row or it is an yellow in a row. And if you look at the execution unit also, it contains instructions belonging to multiple program, but given one clock cycle, either it will be red or it will be yellow, and that is known as multi-threading. So I will rephrase multi-threading once again. Imagine you have multiple programs that is stored in your main memory, and your processor has a lot of functional units. Sometimes all the functional units may not be needed as far as one program is concerned. So in one clock cycle, I bring, let's say, 4 instructions from one program A, issue it, then they are going to execute. In the next clock cycle, rather than fetching from A, I am going to fetch from B. So any dependency between instructions of A, because of this context, because of the switching between instructions, that also will take care of your normal stalling. So this switching that happens, and that is what is known as multi-threading. So if you look at the hardware, certain clock cycle hardware is being used by program A, certain other clock cycle this hardware is being used by program B. So this concept of multi-threading is very important. Let us say there are 4 functional units that you have. So in each cycle, some of the functional units are being used. Wherever you have white, that is basically empty. Now multi-threading means for some time I am running this program A, which is shown by dark red color, and some time I am running program B, which is on a lighter gray shade. So if the switching between them, let's say I am going to run for 5 clock cycles and then I shift to B. So A is operated on 5 clock cycles, then I operate on B for 5 clock cycles. So if the switching from A to B is after few cycles, then I call it as quartz multi-threading. And fine multi-threading means that every cycle there is a switch. I am not going to operate on program A only for next few clock cycles. So if the switching between the task is very frequent, we call it as fine-grained multi-threading. If the switching is not that frequent, we call it as coarse-grained multi-threading. We are moving into the next level of superscalar processing. So this is known as symmetric simultaneous multi-threading or hyper-threading. In this case also, we are bringing multiple instructions, but if you look at, I am going to issue 2 instructions of red and 2 instructions of yellow. That means in a given clock cycle itself, multiple instructions I am going to handle. This is known as hyper-threading. Now let us say what is the difference between hyper-threading and multi-threading. In a multi-threading, what we do is, you bring 4 instructions of program A, you decode 4 instructions, and then you are going to give. Let us say there are 10 execution units. I cannot satisfy all this 10, because my instruction A or instructions from A may not be needing all these functional units. Now, can I do little better? Can I bring 2 instructions from A? Can I bring 2 instructions from B? Mix it together, issue it together, such that if I look at my functional units at any given point of time, it consists of instructions from A as well as instructions from B. This hybrid mixing is known as hyperthreading, and it is one of the most popular technology that has been used in almost all the latest processors that we are using in our laptops or in desktop PCs, and that is all about hyperthreading. So, this is a comparison chart where on the left side we have a superscalar processor. Superscalar means multiple instructions are running parallel. So, wherever you see this blue color, these are all instructions that is running parallel. And given a clock cycle, there are 2 blue instructions. Here there is only 1 blue instruction. So, this instruction will go through all these functional units. At the end, it is going to come out. Lot of slots are wasted. Now, if you look into what is fine grained multi-threading, I am not handling with only blue program, I am handling with many different types of programs. So, I go to blue, I go to red, I go to yellow, then green, then violet, then only I come back to blue. So, at every cycle I switch between many of them. In sometimes I am able to make use of all the 4 functional units like this, but in some time only 3, still I have slot wastage. This is called multi-threading. Now, the same multi-threading, rather than switching every cycle, let us say I continue with blue for 3 or 4 cycles, then I switch to red for 3 or 4 clock cycles, then to yellow, then to green, that is called coarse grained multi-threading. And multi-processing means I am running blue and I am going to run your red in 2 different processors. So, this is processor A and the other one is processor B. Both A and B are going to access the same memory, and that is known as symmetric multiprocessor. And the last one is simultaneous multi-threading. At any given point of time, different functional units will have instructions from different instruction stream, and that is known as simultaneous multi-threading or hyperthreading. So, this slide gives you an overall picture about what is the difference between conventional superscalar versus fine-grained multi-threaded processor versus coarse-grained multi-threaded processor versus symmetric multiprocessor and hyper-threaded processor. And with that, we come to the end of today's lecture, wherein we learned about what are the extreme optimization cases with speculation, and then how you do multiple issue, the concept of super pipelining and superscalar processors, we learned that, and a concept of VLAW, very long instruction word, wherein compiler is going to take a sequence of instruction, pull it together wherever there is no dependency and issue it as a bundle. We learned about superscalar processor in general and symmetric multiprocessor, then about different types of multi-threading, fine grained and coarse grained, and we concluded with what is hyper-threading. Thank you.